Okay, you can hear me well? Yeah. So, hello everybody. So this second talk for today is going to be on another feature implemented in EPW, and this deals with calculation of superconducting properties. So that's the outline of my talk today. I will give a brief overview of superconductivity milestones, both from experimental point of view and the theoretical point of view. Then I will briefly describe the BCS theory and the Macmillan formula for critical temperature. And the main part of my talk will be centered around the Migdal-Eliashberg formalism for superconductivity. And then just briefly, again, I will mention another first principle method for calculating superconducting properties. And I will finish the talk with two recent examples of applications of EPW on some layered materials. So Feliciano has already mentioned in his talk yesterday about superconductivity. So this is an old phenomenon that was discovered by Cameron Ons in 1911 in mercury. So in this case, it was found that the the current, the resistance basically becomes zero when mercury is cooled down at about 4 Kelvin. So this was followed by many milestones in superconductivity research. And for the reason, like while a lot of experiments have been performed, was because we want to have superconducting materials with much larger critical temperature for practical application. And ideally, we should have something which is at least 77 Kelvin at ambient condition, yeah, because this is 77 Kelvin is the boiling temperature of nitrogen, and nitrogen is abundant. It's abundant and relatively cheap. So by 1780s, it was there was an increasing conviction that superconducting materials have a temperature not exceeding 30 Kelvin. So the discovery of superconductivity in a compound of lanthanum, copper, oxygen, so these are the copper oxides, was really a paradigm discovery. So in these materials, the superconducting critical temperature soon exceeded 77 Kelvin. So it was believed that they will be useful in practical application, but unfortunately, these materials are ceramic and it's very hard to manufacture them into wires. Something that I forgot to mention, mercury and all the superconductors that were discovered until 1986 were phonon mediated. This was a new class of superconductivity, and in this material, the coupling doesn't come from the electron-phonon interaction. Another breakthrough in superconductivity research was the discovery of phonon-mediated superconductor with 40 Kelvin in magnesium diboride. Yeah, so this is a simple system that was in the lab of many experimentalists, and at the time that was considered a really breakthrough and gave hope that phonon-mediated superconductors with even larger critical temperature would be discovered. And I will come back to this point in my example later at the end of the talk. Another breakthrough was in 2008 when superconductivity, again, non-phonon mediated, unconventional superconductivity was found in iron selenide. So this will open the iron age of superconductivity. And then I would say this was followed by discovery of high TC superconductivity in the hydrides. So that's the example that Feliciano has shown. Yeah, so this had a high TC of about 200 Kelvin, but it requires very high pressure, about 150 gigapascal. Yeah, so this requires specific experiments with diamond anvil cells, and the quantity of the material that you get, it's basically just tiny. And the discovery in this class of material has culminated now with the room temperature superconductivity that was found in 2020 in a compound made of carbon, hydrogen, and sulfur. And as far as I know, the crystal structure is still not yet known. So this is one suggestion of one of the possible crystal structure configuration. Yeah, so this is kind of the main milestones in from the experimental point of view. So now let's see what has happened quickly on the theory side that has enabled nowadays to basically it made possible or feasible calculation of superconducting properties with anisotropic resolution in phonon-mediated superconductors. So I'm just stressing out all the talk that will be done today is relevant for superconductors in which the mechanism is driven by electron-phonon interaction. And of course, as I said, so the first theory of superconductivity was developed in 1957 by Bardeen, Cooper, and Schiffer. So this is called the BCS theory. And I will just briefly mention it on the next slide. And this, as you will see, it's a phenomenological model. And that was followed by a first principle approach just 3 years later. Unfortunately, as you will see, this equation have a quite complicated form, and it was not possible to use them in an anisotropic form in first principle calculations due to the computational expense for basically up to about 10 years ago. Nevertheless, the development of DFT and DFTP have enabled application of this Eliashberg theory in a simplified form, the semi-empirical form using Macmillan expression, and that was done for many years, starting, I would say, from the 90s, because the electron-phonon coupling was available in Quantum Espresso and Abinit codes. So now what was crucial for Eliashberg formalism was the development of maximally localized Wannier functions that we already learned about on Monday and Tuesday, and then the methodology developed by Feliciano in 2007 to do interpolation of electron-phonon matrix elements based on this Wannier Fourier interpolation technique. And as you will see today, this has enabled solution of the Eliashberg equations in the anisotropic form. Just briefly, as I said, I will want to mention that there is another first principle approach, and I will have a slide on this, which is called superconducting DFT. And as far as I know, there is an open source code called SCTK that allows calculation of superconducting properties with this methodology. So now let's see this basically BCS theory. And so the BCS starts from the assumption that there must be some form of interaction between electrons that counter interacts basically this strong Coulomb repulsion. And in phonon-mediated superconductors, the name suggests this interaction is due to the electron, between the electrons and phonons. Yeah? So as electron travels through a crystal, it creates, it attracts the ions, and it creates a deformation potential, and a second electron is going of opposite momentum. It will be attracted in this region, and in this way, the two electrons become strongly correlated. So from a diagrammatic picture, it means that the two electrons scatter on each other by exchanging a virtual phonon, and they go from this, a pair from with momentum k minus k, goes into another pair k prime minus k prime. So you see that one electron emits a phonon, and this is absorbed by the second electron. And that I said, and for this interaction to take place, it means that the new pair k prime needs to be unoccupied and in the vicinity of the Fermi surface. Sorry. The main normal metal, and this gap this gap is temperature dependent. Yeah, so this gap can be found by solving this. Sorry, I have tears, not because I'm crying, it's because of the cough. Just so you know. This gap, it has this temperature dependence, when where this V is the pairing potential. Yeah, so if you were to calculate this gap, you see that it has this temperature dependence. It's maximum at the 0 temperature, and then it becomes 0 at the critical point. So the key thing is that once you are in the superconductor, you get back in the normal state, this gap is going to close. Yeah, and the reason why this gap it forms is that these Cooper electrons now don't behave like fermions; they behave like bosons. So it means that you can have more than 2 electrons in the same state. So as a result of this, you'll have this change in the density of states here, where you see this peak, which means that the electrons that have initially occupied this area are now accumulating at the edge of this gap. So PCS, as I said, describes in detail the phenomenology of superconductivity, but this remains still a descriptive theory. In other words, it's material independent, and it gives this general equation for all superconductors. Yeah, that the ratio of the gap at 0 Kelvin to the critical temperature is 2 delta 0 is 3.53. And another important thing is that it does not account for the retardation of the electron-Phonon interaction. So in other words, it considers that the interaction is instantaneous, and that's in general, this is retarded. Yeah, because for the phonons, for the ions, it takes a while after they deform to go back to their equilibrium position. So now, how can we calculate TC beyond BCS? I have already mentioned that for many years, this was possible, could be done using an empirical formula that was very popular. So that initially was derived by Macmillan and later on refined by Alan Dyne's formula. And in this expression, lambda is the electron-phonon interaction. And this is the term that we can calculate, we can calculate it also with quantum espresso or Rabinit. And the mu star here, this describes the Coulomb interaction between electrons. And in general, this is a parameter which is approximated. And for most material, it falls at about 0.15. Yeah, so it's somewhere in the region of 0.1, 0.2. So advantages of this thing and why it has been used for many, many years was that it can be easily calculated quantum espresso, and it works reasonably well for isotropic superconductors. Yeah, at the end of the talk, I will show a few examples where this method, in fact, fails, and this is the case of layered materials. In most layered materials, this is not going to work very well. So the central part of my talk, as I said, will be centered around the Migdal-Eliashberg formalism. And this is the easiest way to be described this formalism is to use the Nambu-Gorkov representation. So in this case, we are going to use a generalized 2x2 Green's function, which will be used to describe the propagation of electrons in the normal state and the superconducting Cooper pairs on an equal footing. Yeah, so that's similar, like this, it reminds you of what Feliciano was showing yesterday. The only difference is that right now, this psi is a 2-component field operator that has C and C dagger. And the one thing that you should notice here that this has momentum K, and this has momentum minus K and opposite spins. Yeah, so this is that will allow us to form these Cooper pairs of with electrons of opposite momentum and spins. So if you now plug in this field operator in the expression for the 2x2 matrix Green function, you can write it in a matrix form. And in this case, we can notice that the diagonal terms, they are called the normal state Green function. Yeah, you can see that exactly the same term that Feliciano was showing. And now you can, in this case, you have the electrons are both with the same momentum, the same spin. Yeah, so they basically you create and then you destroy an electron. And then the non-diagonal terms, these are called the anomalous Green function. and describe Cooper pair amplitudes. You can see here that, as I pointed out, that the electrons have opposite momentum and opposite spin. And here you destroy, and then you create, let's say, a pair. Yeah. So, and the key thing is that in the normal state, these off-diagonal elements are going to be equal to 0. Now, it is more convenient to move from the tau to imaginary frequencies, and this can be done remembering that this function is periodic in tau, and we can express it in a Fourier series in the following form, where this I omega j's, these are called Matsubara frequencies. And yeah, so they have this expression where here T is the temperature and J is an integer. So if we write it in a more compressed form, we will call these diagonal terms J, the other Green's function, and the non-diagonal, the anomalous Green's function, they are in general labeled with F. So the key thing right now is to find, basically, in order to solve, as we will see, the Algebra equation, we need to find an expression for this Green matrix. And the starting point is we need to have a self-energy, electron self-energy. And for the superconducting, in superconductivity, again, we are going to have two terms, almost like in the normal state. But again, the difference being that now we have matrices instead of just one component. Yeah. So the first term is the Fang-Migdal self-energy that was introduced yesterday by Feliciano. Yes. So this vertices here, these are the electron-phonon matrix elements, and D here is the dressed phonon propagator, and G is the Green functions in the interacting Green's function in the normal state. And then we have a second term, which is the screened Coulomb interaction. Yeah, so this is the same as the GW self-energy. And in this case, we are only keeping two terms, one that comes from the electron-phonon. So this is called the Migdal approximation in the normal state. So basically it means that we neglect all phonon vector corrections on the assumption that the ratio, square root of the ratio of the electron mass to ion mass is small. Yeah, so this is of the order of the ratio of the Debye frequency to the Fermi energy. Of course, in materials where electron and phonons energy are comparable, non-adiabatic effects would be important, and this approximation may fail. And also in this case, for the screen-Coulomb interaction in general, there is not an equivalent approximation, but in general, you only keep just the first term. So if we now start from this expression for the self-energy, now I just write written as an equation. I got rid of the here I just put this sigma, replace it with J. Oh, sorry. And then if the first approximation that we do, we replaced the dressed phonon propagator with the bare phonon propagator. So in other words, we don't have any we don't take into account any renormalization of the phonon frequency. Yeah. So in general, the phonon frequency can be renormalized from electron-phonon interaction, but also can be renormalized from phonon-phonon interaction. Yeah. So that's kind of the first approximation that we made here, that we only use the bare phonon propagator. And this allows, with this approximation, we can now introduce what we call the anisotropic electron-phonon coupling strength. And this is basically the key quantity that we calculate with EPW, yeah, because here this is nothing else but the electron-phonon matrix elements. And so I'm just plugging in here, so I'm rewriting the equation in this form. Here I should mention this tau. I forgot to mention these are Pauli matrices. So now we still don't have. We still need an expression for J in this self-energy. So the way to get an expression for J, we need to remember that it obeys a Dyson equation in the Matsubara space. So in this case, G naught is the non-interacting electron Green's function. Yeah, again written in terms of the Pauli matrices. And for sigma, we can come up in the first place, and it is going to come evident in the next slide. We rewrite it as a linear expansion, again, in these Pauli matrices as a function of 3 terms. So this Z is the mass renormalization function. That's the same kind of quantity that was introduced yesterday. This chi is nothing else by a simple energy shift. And this delta is our superconducting gap function. Yeah? So if we now replace the J naught and sigma here, and then you do an you invert this matrix, you are going to find an expression for this matrix J that has this diagonal and non-diagonal terms. Yeah. Remember again, the diagonal terms. These are will describe single particle electronic excitation in a normal state, and the non-diagonal terms will describe the Cooper pairs in the superconducting state. So now that we have an expression for J, we can go back in our original expression for the self energy. Yeah, so these are kind of a few intermediate steps. Like if you don't, you can go back and try to follow the math if you couldn't do everything at this point. But right now, what we ended up with, if we replug in here G in sigma, we have an expression for sigma in terms of tau 0, tau 3, and tau 1 that are labeled, sorry, that the coefficients are Z, basically chi and delta. And then we remember our original expression. And if we just equate the coefficients of every matrix, we basically end up with the 3 equations that we need to solve. Yeah, so these are the anisotropic Migdal-Eliashberg equation. And as you can see that we both on the left and on the right, we have Z and K, chi, and delta. So this means that we need to solve them self-consistently. So this is the most general form of the anisotropic equation. It is called full bandwidth description. And we will see later why we call it like that. Now, if we assume that the chemical potential is not fixed in our system to the Fermi energy, then we need to add a fourth equation for the electron number. And this needs to be solved every time for when we do this self-consistently. Yeah, so at every self-consistent step, we need to also calculate this. We need to impose the condition that the electron number remains constant to find the chemical potential. One thing that I should point out here is that the Coulomb term only enters in this equation for delta, and basically it was already accounted in the other cases in the normal state, and to avoid double counting, it only enters here. And the last thing that one thing that I should also point out here, and I forgot to mention before, is that the electron-phonon interaction, or the scale on which the electron-phonon interaction takes place and the Coulomb interaction takes place are very different. So it means that the sums over the Matsubara frequencies, the J prime signs here, they need to extend to different cutoffs. Yeah. So for the electron-phonon interaction, the sum is it's on the scale of the phonon frequency. So this is of the order of milli-electron volts, but the sum over the Coulomb term, it's of the order of the plasma frequency. Yeah. So this is order of electron volts. So that makes means that the computation is going to be more expensive, and that's the main reason why for many years and that's the implementation that we currently have in EPW, that the Coulomb interaction is approximated to a semi-empirical parameter, as we will see on the next on this slide. Yeah, so this dynamically screen Coulomb interaction will be embedded into this semi-empirical pseudo potential that we call mu star, And that's an input variable right now in EPW. Now, solving this equation would be quite computationally expensive. So until this current version, we didn't have this this set of equation implemented, but this is the new implementation that we now it's available in the code. And one way to simplify this equation is to assume that the interaction takes place around the Fermi surface. So this means that we can perform an integration here. We can do it analytically, and in that case, we can show this chi term, the shift in the Fermi in the energy to be 0, and the equation can be reduced only to a set of 2, and this is implicitly also 0. And this is what we call the standard approximation, or the Fermi surface reduced anisotropic equation. So this assumption, this simplification was done under the assumption that the density, electron density of states in the vicinity of the Fermi level is constant. Yeah, so we don't have peaks. And basically, we are doing this by introducing here some delta function and resolving the integrals. So you see that the difference now is that we have these delta functions that enter here. So it means that these quantities are only calculated or are only valid, this equation, in the vicinity of the Fermi surface. So, so here I'm just, it's the same equation. I'm just rewriting now, also using, as I said, this approximation that the Coulomb interaction was replaced by this semi-empirical pseudo-potential mu star. And now, in order to solve this equation and also the other form, the full bandwidth, as I said, the key quantity that one needs to calculate is this anisotropic electron-phonon interaction. Yeah, so that's the key quantity that enters in this equation, and that's can be done efficiently with EPW. In principle, you can also, I said that right now you can do a Coulomb pseudo-potential mu star, which is a semi-empirical value, but in principle, you can estimate this Coulomb pseudo-potential ab initio, and we have done this in a few studies. So the way we did it, it was the Coulomb interaction was calculated with the Sternheim-Merge W code, and then we used this model Anderson pseudo-potential to estimate mu star. Yeah, so by replacing the Coulomb interaction with this mu star, what we basically effectively do, we reduce the we screen the electron interaction in such a way that it can be solved. It's basically is reduced at the same scale with the electron-phonon interaction. Yeah, so then the sum over the Matsubara frequency, we can use the same cutoff both for electrons and electron-phonon and electron-electron interaction. So that, just to summarize a bit this part, just what we have to do if you just solve in this within this approximation, the Fermi surface restricted, you still need to solve this equation self-consistently at every temperature. Yeah, so at every T here you will need to solve this system of coupled nonlinear equation. And in order to properly describe the anisotropic effects, you need to evaluate this on relatively dense K and Q meshes. And then you also need to make sure that your calculations are converged with respect to this Matsubara frequency. And typically, you need to use a cutoff of order of 1 electron volts, or at least, let's say, 5 times your largest phonon frequency in the system. And then if the equations are solved within this approximation, you need to remember that the Z and delta are only meaningful for the states near the Fermi surface. Yeah, so it will be a Fermi window, and these quantities will only be relevant within that Fermi window. So now, for practical implementation, these, as I said, are solved on the imaginary frequency axis. But if you want to calculate quantities that have spectral representation, for example, if you need the quasi-particle density of states or the single particle excitation spectrum, then you need to go from the imaginary frequency axis to the real frequency axis. And this can be done directly by solving the Migdal-Eliashberg equation on directly on the real frequency axis. I haven't shown any formulas for this because this is not implemented in the code. And the reason is why this is not implemented, because it will require calculations of principal values, integrals, and this is very expensive computationally. Yeah, but the way that we do it, we solve the equation, as I said, on the imaginary axis, and then we do an analytic continuation to the real axis. And this can be done very cheaply computationally using the approximants, or in a more, let's say, more accurate way, you can do an iterative procedure, but this is very heavy computation. So now, if you have the z, delta, and all the quantities on the real space, you can we have the single particle green function of the real axis, and let's say in the first place we can analyze the poles of the diagonal elements of J to give the elemental excitation of the superconductor. Yes, so the diagonal elements of this will be here. Remember, these are matrices. Yeah, tau no, tau 3. These are 2 by 2 matrices, and this term is the diagonal term. And the pole position of this diagonal term is, you can take the denominator and make it equal to 0. And in this case, you E is a complex quantity. Yeah, so the real part is the quasi-particle energy renormalization for the superconducting pairing, and the imaginary part is the quasi-particle inverse light time due to the superconducting pairing. Yeah, so these are again the same kind of notions that were introduced yesterday for the normal state using the electron self-energy in a normal state. Now, at the Fermi level, you can see that if E and K is equal to EF, this term is equal to 0. So this identity allows us to obtain delta, so the leading edge of the superconducting gap. So this is nothing else but the binding energy of electrons in the Cooper pair. And if you plot this quantity, so you basically evaluate this at every temperature. If you plot this quantity as a function of T, you will get what we call the superconducting gap function as a function of temperature. Yeah, so this plot is an old plot from our original implementation on MGB2. And as you can see, you can just solve these equations self-consistently. You naturally get that MGB2 is a 2-gap superconductor. Yeah, if you were going to evaluate this, the TC using my Milan formula, you will only get one number. In general, you will get something like around 20 Kelvin for MGB2. And of course, you are not going to have any information that this is a 2-gap superconductor. Yeah. Also, if you can also do some other things, you can get the superconducting quasi-particle density of states. This is related to the imaginary part of the diagonal elements. And it's in the BCS limit, if in this expression for G11, if you take Z, the renormalization, mass renormalization function to be equal to 1, and you do this integral, you will find, you can get this expression. And here I'm just plotting again from this older study. This is the quasi-particle density of states. And you can see there are 2 gaps. Let's just focus on the black curve here, calculated at 15 Kelvin. You can see this is the first gap on the pi states, and this is the second gap in MGB2 on the sigma states. Yeah, so this is the smaller gap that you are seeing here, and this is the corresponding to the second gap on the sigma states. And you can also, if you calculate as a general of another omega, you can also get the spectral function. And you can see from this plot, this will be, this is crossing the Fermi level. Yes, so there is no gap. So this will be how the spectral function in calcium C6, calcium C6 looks in the normal state. And then if you were to calculate the spectral function in the superconducting state, you will get this gap. So maybe it's not so easily seen, but here this is like this, and this is like this. So this is exactly what I was showing in the beginning in that simple picture of opening a gap in a normal state of a metal. Yeah, so you can nicely get this if you calculate the spectral function. Yeah, so this is from an old study by Sana and in Gross's group on calcium 6,6. So just to kind of summarize here, that's kind of the end part of the theory, is that the Migdal-Eliashberg formulas has predictive power. It's material dependent. Yeah, so you can apply it on any material. It accounts, I forgot to mention this, but it accounts for retardation of the electron-phonon interaction. And the main thing is that it works for multi-band and anisotropic superconductors. In the current implementation, we still rely on NuSTAR, but hopefully this will get rid of this approximation soon. And in the next, maybe in a year, next year or so, we'll have a new implementation where we are not, we won't have to rely on this parameter. So I said that there is an alternative method for calculating superconducting property for first principle, and this is density functional theory of superconductors. And in this case, what you need to solve is this gap equation, which is reminiscent of the BCS gap. So the only thing is the difference is that here there is an additional term. This has basically the mass renormalization function, and then the kernel here, it replaces the model interaction in the BCS model, and this kernel contains both the electron-phonon and the electron-electron interaction. Yeah, so a big advantage of this superconducting DFT is that it treats both the electron-electron and the electron-phonon interaction on the same, on an equal footing. Yeah, so there is no NuSTAR approximation in SCDFT. I would say one, at least till a few years ago, I think one, I guess, issue or let's say problem with this was that there weren't many functional available to describe the electron-phonon interaction. Yeah, so if so, in order to for superconducting DFT, you need to develop new functions. Yeah, so if you take the functionals that are now existent, let's say in quantum for quantum espresso or Rabinit, those of the potential are not going to be very good. Yeah, you need to develop new functionals. And as far as I know, there are just two sets of functionals available, both coming from Gross's group, but in the 2020, they developed new functionals that I think are working pretty well. And of course, as for the Eliashberg equation, you need to use dense K and Q meshes if you want to look at anisotropic properties. So that's basically the end of the theory part. I think, okay, I should speed up because I'm a bit slow. So this second part, I need to discuss give a few examples. And the two examples that I'm going to show today are some relatively new results. So the first example, it's on a layer compound. And as I said, this kind of study was, it started 10 years ago, and then just recently we revisited, and it was motivated by finding new superconductors with MGB2 type superconductors. Yeah. So as so the discovery of superconductivity in MGB2 in 2001, as I said, with a TC of 40 Kelvin, triggered many experimental and theoretical works that aimed at finding MGB2 type superconductors with increased critical temperature. And you will find many studies in this area. I'm not going to, my goal here is not to review them, but just to give a few pointers. But in general, what was found is there are many predictions, and a lot of prediction either found if, let's say, the critical temperature was predicted to be much higher than MgB2, it turned out that those materials are not stable. Yeah, so they are not synthesizable. Or if it was found, like let's say compounds that were found to have to be synthesizable, in general, had the critical temperature which was lower than the one found in MgB2. So that's an study by Alexei Kolmogorov and Stefano Curtarolo, that in 2006, they were looking to find basically MgB2 type superconductors, and they came up with this system in the lithium boron binary, that it has it's a honeycomb layer. Yeah, so here these are the boron layers that have the same structure as in graphene, and the only difference, if you know the crystal structure of MgB2, is that you have an extra layer of these lithium atoms in between the boron layers. So once this material was shown to be stable, there were a couple of theoretical studies, one from Alexei and Curtarolo in collaboration with Matteo Calandra. I don't have a reference here, and one coming from Igor Smazin's group, in which they looked at the superconducting properties of this material, but using basically the just the Macmillan formula or Allendine formula. So they did this using an anisotropic model, and they pointed out what were the key electronic features that drive superconductivity in this material, which were similar, some were similar to MgB2. Yeah, the key thing is that you will have this unoccupied, hole occupied sigma state, which is a key feature in magnesium diborane. And you also have something like in graphite intercalation compound, which are these lithium states, yeah, that have this parabolic band. These are nearly free electron states, and this is the main driving interaction in, for instance, calcium C6. So it seemed that like this material basically had both key ingredients that will make it a high TC superconductor. Yeah, it had the key ingredient from MgB2, whole doped sigma states and NFE states. But it turned out that when they calculated the critical temperature, this was with Macmillan, this only fell in the category of basically 10, 15 Kelvin. So we just this year, we decided to review this system, and we applied the anisotropic formalism. So I forgot to mention that this compound has been synthesized in 2015, so we can synthesize a relatively low pressure of about 20 Kelvin, and it can be in its metastable ambient condition. Yeah, so it can be brought down to zero pressure. And when we now apply the anisotropic Migdal-Eliashberg formalism, we found that this is basically a two-gap superconductor, and the critical temperature should be larger than initially predicted, about 3 times larger. So this is with a mu star, for instance, of 0.1, and it goes down to about 32 Kelvin with mu star 0.2. This is still below MgB2, but what I want to point out here is that if you have a layered material, if you want to have accurate prediction, the Macmillan formula is not going to be enough. Yeah, for layered materials, you really need to go beyond this approximation and do an isotropic calculation. And just to summarize here, in this case, we looked at so this is MgB2, and we look at a few other, we scan basically this lithium Mg phase, and we found some additional phases. These are all metastable. We only look at them to see what will be beneficial superconducting features. And in all these cases, we found that you basically need to look at anisotropic properties. Yeah, so this will be what you will get with Macmillan, this black dots with a cross thing. And that's what you will get if you, let's say, solve the Migdal-Eliashberg equation in the isotropic form. This should be close to Macmillan. And that's what you will get if you solve the anisotropic Migdal-Eliashberg equation. Yeah, so you will really underestimate a lot if you just based on Macmillan. Yeah, so this will be somewhere MGB2, depending on different mu star, falls between 40, 50, just for comparison. The second example, I'm just mentioned a bit briefly, is regarding this new implementation of the full bandwidth full bandwidth approximation. Yeah, so the other calculation was done using this Fermi restricted description. So here, one thing when you need to solve its equation is right now, since we don't have this delta functions entering in the equation, it means that you need to you may need to pick larger Fermi windows around around the Fermi level. And in niobium disulfide, niobium diselenide, and the same would be the case for niobium disulfide, are good cases to look at, because as you can see, in the vicinity of the Fermi level, there is this peak. Yeah, so the dashed line here, this is the Fermi level, and this is just a peak that appears just below the Fermi level. So here I just want to highlight that the key aspect that we wanted to understand here is not to get the TC, but kind of to see the effect of compare this full bandwidth and the FCR approaches. So that shows that, so in this case, a window of about 0.4 seems to be already enough to capture this peak. And so that's the solution here with the full bandwidth. And we found, as for niobium disulfide, and this is known, that this has a gap, a single gap, but which has contribution from two parts of the Fermi surface. Yeah, so the lower gap comes from states around the gamma point, and the upper part of the gap comes from states around the these K pockets. And if you were to compare, now we also compare the this fixed chemical potential with a variable chemical potential. You remember when I had those either solve 4 or 3 equations in this in this approach, found that if you were to include to have this variable chemical potential, then you need larger cutoff frequencies in your Matsubara summation. So here I showed the result for 1.2 EV, but already at 0.8 this was converged, but this was still double the cutoff frequency that it was required with the fixed chemical potential. And you can see there is also some slight difference in the final TC. Then the last plot that I'm showing here is that this is the comparison between the full bandwidth and this Fermi surface restricted. So in this case, although there was a very sharp peak in the dose, we didn't find that this has a significant effect. But of course, as I said, this is only the first study that we have. So we need to more systematically look at materials that have large variation in dose around the Fermi level to understand, like to get a picture of when this full band weight method is more appropriate. One thing you need to keep in mind that this is approximately 30% more expensive than when you do this restricted Fermi surface approach. So just last plot that I want to comment here. So this plot also shows the same approach, but instead of using a uniform grid of Matsubara frequencies, now we have in the code implemented what we call a sparse approximation. Yeah, so we take out some of the Matsubara frequency point towards the upper limit of the cutoff. And this works relatively well. And I think you have a speed up of about 40% compared to the uniform grid mesh. So my take-home messages for this this part of our code is that we can obtain measurable superconducting properties with an isotropic resolution using these formulas, but to solve this equation, invariably it requires a fine sampling of the electron-phonon matrix elements across the Brillouin zone. And these are a few references. Some of them are quite old, but these are the main, let's say, main references on theory with the Cooper-Schiffer formula, then the Islandines formula for TC, and then some of the nice papers, if you are interested, by Scalapino and Allen and Mitrovic on the LER performance. So I think with this I'm done for and wait for questions.
Hi, thank you for your talk. Can you elaborate a little bit on the treatment of flat-band superconductors and what's definitely to obtain accurate results?
Sorry, can you repeat the question one more time?
Sure. Treating flat-band superconductors, like high density flat-band at the Fermi surface.
So there you are expecting to have a high density of states, probably. Sorry, which one is not working? This one. So you will have a high density of states in the vicinity. Still not working. It stopped working. Maybe I pressed. Maybe I switched it off. So that is expected to have a high density, so a peak in the density of states at the Fermi level. So I would think that this new implementation may be more appropriate to use. Yeah, but again, I think it's really, we haven't systematically looked. So that's something that we are interested in doing next, to take variable, different systems with different configuration, let's say, of the density of states, and see in which cases this seems to be important. Yeah, but probably some of the hydrates, I suspect that if that's where you are hinting, in some of the hydrates it could be important. There is some study in Arita's group a few years ago where they looked at one of the hydrate, maybe even H3S, and there is a claim that this could be important.
Thank you. Question?
It's very interesting that you say that the inotropic effects are particularly present for these layered materials. You can't get layered materials without pi bonding, usually.
Sorry?
You can't get layered materials without pi bonding, usually, certainly with carbon, boron, or beryllium. And we don't know yet of a system where pi bonding is a strong sigma bonding. So you would always have weaker pi interactions than sigma interactions. So you could perhaps say more generally that you get anisotropic contributions if you have different chemical interactions at the Fermi surface. So has there been an attempt to relate the size of the superconducting gaps, the different superconducting gaps, to the relative interaction strengths that are well documented, sigma and pi interaction strengths?
That's an excellent question. Not as far as I know. Sorry, as far as that's an excellent question. As far as I know, no, but you are right. Yes, this should be dependent on exactly the strength between the sigma and pi. And what I want to say is the difference in the two gaps. It will be related to how strong the electrons couple to the sigma and how strong it couples with the pi band. So one thing in this compound lithium boron is that it has a, is this working? No, it's not. So one thing that is, it's not, okay. So one thing that is, that makes this lithium boron to have a lower TC than MgB2 is that it's lacking coupling from the pi states. Yeah, I forgot to mention that.
So the anisotropy is always increasing TC, right?
Yes.
No.
Thank you for a wonderful talk. I'm wondering, is it currently possible to choose the Einstein theory numerically, including spin orbit coupling?
It is implemented with spin orbit coupling in EPW. Yes, you can do that.
What about time emergency tree, like including the M field?
Not right now, just spin orbit coupling.
Yeah, thank you for interesting talk. I just wonder, because in the PCF, in the full term, all the superconductivity in that way. Have you ever tried mechanism to study PV, like uranium chloride?
So this implementation is just for S wave superconductivity. I haven't. Thank you.
Okay. Questions?
Yes, two from Zoom.
Two from Zoom.
Okay, so we have two questions from the webinar. One is, can we calculate the critical temperature of two-break superconductors by the method which we introduced? For example, YECO.
No, that's related to the last question here. It only works for S. I mean, we only have S gap.
Okay. Then the second question is, what is your best or usual method to predict the Coulomb pseudopotential for maybe the Coulomb interaction for the DC calculations?
What is the best? Can you repeat it again?
What is your best or usual method to predict the Coulomb interaction using the DC calculation?
So as I showed, I mean, in general, in most cases that we have looked at, we just varied mu star between 0.1 and 0.2. But in a couple of studies, we have estimated, I'm trying to get to the slide, mu star using the Sternheimer GW code and use then this Morel-Anderson pseudopotential. There is a study coming from Sana's group, I don't remember the name, but where they estimated mu star for about 10 between 10 and 20 materials, and they found that in most of them, the mu star falls between 0.1 and 0.2, roughly it was 0.15. So I would say that probably for a lot of systems, an average mu star of 0.15 gives reasonable results.
Thank you, Roxana, for a very nice one. Just a quick question. In your later material, why the Margine lines simulation is so off, and why they have opposite trend to the actual calculation?
Very good question. So the reason for that is Islandine is basically gives the same result as if you were to solve the isotropic equations. And the reason for that, just simply, if you look at this, if you will do isotropic calculation, you will get an average gap, which is kind of in between these two. And if you just solve this, you will get roughly half of the TC. Yeah. So as you can see in this plot, the isotropic calculations are quite close to the Macmillan or Allandine. Yeah, and it's basically because you are more or less averaging the gap. So that's, I guess, coming to the other question. If your gaps are very close, you are going to get a reasonable, I mean, a close result if you just do Macmillan or Allandine or isotropic BCS. So here, in this case, since the two gaps, for instance, are the same, your isotropic results are not going to be as off as in MGB2. Yeah. Yeah, an isotropic solution will always be higher than the isotropic solution. Because isotropic,